So this is a tutorial. This is about, we're going to try to keep to the schedule if we can and finish by about 3:15. So it's actually going to be a little less than an hour and a half, maybe an hour, 10 minutes here. This is a tiny glimpse of a 8-hour full day DSM workshop. So it's just got a few of the basics from there. In the full workshop, we get a lot more into the why questions, motivating DSM. We get more into the how to use and apply DSMs to different types of things. But here, it's just trying to answer basic what and how questions. What is DSM? How can we look at it? How can we build a model? So very basic DSM here, a square matrix, same number of rows and columns. As I mentioned earlier today, it's easiest to think of the diagonal cells in the matrix as the nodes in a node link diagram or a network, and then the off-diagonal cells represent relationships. So here we have what's called a binary DSM because there is or there is not a relationship. There's a mark in an off-diagonal cell or it's blank. So those are the only possibilities. Later we get into more elaborate types of DSMs. The other thing about this DSM is that it is formatted in a particular convention of how to read the rows and columns, which is an output from one thing and an input to another thing. So the way you read this DSM is you look at a column, like let's take element A on the left column. We look at that column to see all of the other elements to which element A sends an output. So element A provides an output to elements B, C, D, E, and I, all in that first column. And then we can look at rows to see where elements receive inputs. So row B, for example, element B gets an input from element A. So element A, it's an output. Element B, it's an input. And so that's the first thing to start noticing here in a DSM model, that each node is both a customer and a supplier, potentially. It's both a giver and a receiver, depending on your point of view. And each dot, each mark off the diagonal is both an input and an output, depending on your point of view. Are you the provider? It's an output. Are you the receiver? It's an input. But it's the dot, the relationship, is usually something. It might be a report or a result, some kind of work product, some kind of deliverable, some kind of thing that flows out of one into another. If it's not a process DSM, if it's a product DSM, it could be some kind of connection, some kind of material flow, some kind of energy transfer. So there's all different kinds of potential relationships we might want to model. But here with the DSM, those relationships are directional. Sometimes you'll see what is essentially half of a DSM, called an N-square diagram. And that is just the upper triangular or the lower triangular part of the square matrix. And that shows relationships among the same elements, but it doesn't tell you the direction of the relationships. It just says there's a connection. Here, the fact that A provides something to B with that mark just below AB in the diagonal, you don't have to assume that B is providing something to A. Notice that it's blank above the diagonal there. So here we can capture directionality. So any questions on the very basic DSM here? So you saw this diagram earlier comparing to a node link diagram, so I'm not going to spend a lot of time here unless you've got any questions or comments. So, all right. You may also have noticed that DSM stands for a lot of different things. In this conference even, we call it various things over the years. So what's the latest incarnation, Danilo? Is it dependency and structure modeling here? That's I guess now the official name of the conference, so it's not even just design structure matrix, it's more than that, related things for modeling dependency structures. Dependency structure matrix, decision structure matrix, dependency source matrix, and others. I've seen a lot of different ways to describe DSM. Thankfully, they're all sticking to DSM as the initials. But if you want to do a Google search, you can probably find things in each of these areas. And by the way, there are a lot of other matrix-based methods, some of which are essentially like DSM. So if you're familiar with graph theory or matrix algebra, you might know of things like relationship matrices, adjacency matrices, reachability matrices. A lot of these are similar to design structure matrix methods and techniques. Precedence matrix, precedence map, dependency map, you'll see these terms used quite a bit. Systems engineers, N-squared diagram, as I mentioned, and in the Department of Defense architecture framework, there's something called a System View 3 that's essentially a DSM. If you've used QFD, quality function deployment, sometimes people use an attic or roof on this so-called house of quality. That's essentially half of a DSM. And so there's a lot of matrix-based methods out there, some of which are not DSM. The way to tell is that DSM is always a square matrix, not a rectangle. So there's a lot of rectangular matrices out there that have important uses, but to be a DSM, it's got to be a square matrix. So we'll get to rectangular matrices later, DMMs, domain mapping matrices. So DSM, as I mentioned earlier, is not always the best tool to use for a problem. There are a lot of problems where you're better off using some other tool or method. So I happen to like DSM, but I don't think I should always use DSM for every situation. So some people, when they first learn a new tool, they want to go use it on everything. But that's not the point here. So the point is, when should I use DSM? When will it be most likely to be the right tool for the job? Well, if you can take advantage of its strengths, that's when you would want to use it. So what are its strengths? Well, one is representation. It's a nice, visually appealing, fairly concise way to show a network, a set of nodes and their relationships. And as I mentioned before with the node link diagram, it can get messy. The arrows start crossing over each other. It gets hard to see all of the relationships, and then especially to infer indirect relationships among those. And then it's sometimes hard in node link diagrams and other representations to see cycles especially, but even modules sometimes. So there are ways to take a node link diagram and use groupings or colorings or things like that to help try to illuminate modules. But DSM is it's very easy to show those with blocks or shading or so forth. So representation is one big reason why you might want to use a DSM versus something else. Another is that the analyses that we've often highlighted with DSM, clustering, sequencing, they tend to correspond to these two important types of patterns that we like to see or find. And so it's not that you couldn't do these analyses in other formats. You certainly could. But sometimes the results of those analyses, coming back to modules and cycles, are easier to see, easier to get an intuition for what's going on when you're using a DSM format. So those are possibilities for when DSM can be helpful. Pretty much anything you can do in DSM, you can also do in some other format or with some other method. So it's not to say that by using DSM, you necessarily can do a lot of stuff you could never otherwise do. But I think with complex systems, often it's the way you do something that has a breakthrough or has an advantage for helping someone better see, better understand what's going on in the system. Maybe highlight some critical patterns that have implications for performance. And so that's where DSMs seem to have found the most benefit when they could fit those advantages. So there's a book on DSM that Steve Eppinger and I co-wrote. Steve will be back later, but he didn't need to see this tutorial again himself. But I do have an example of the book here. If anyone's interested, feel free to take a look. And I have a couple of those, if anyone's interested, that I'd be happy not to take home with me. So talk to me if you're interested in one of those. But this book is broken down into 10 chapters, and you see here that they're in couples, these chapters. So the first of the 2 chapters introduces this type of DSM, and then the second of the 2 chapters gives a bunch of case studies, a bunch of examples. So 2 main types of DSMs I'll start with, static and temporal. Static DSMs take like a snapshot in time of a system. Typically they get applied to products and organizations. So the assumption with a static DSM is that all of the nodes exist simultaneously at the same time, and we look at the relationships. So obviously products and organizations can be dynamic. They don't have to be static. So if we want to capture some of the dynamics, we may need to look at multiple DSM pictures over time. Temporal DSMs, we assume a time relationship among the nodes in the system. Some nodes are what we would call upstream. Some nodes would be what we call downstream, like a process. All of them don't necessarily exist at the same time. Some happen before or after other nodes. So that's a temporal DSM. And then multi-domain matrices, you saw me refer to those a bit this morning, and at the end of this presentation today I'll mention a few more. But that's where we start taking DSMs and putting them together. Maybe different types of these DSMs and start combining them. So I should say aggregating them, not necessarily intermingling them, but just putting them next to each other and sometimes doing an analysis on one that might also change the other one. So these are some examples of some types of DSM applications or models, but it's not comprehensive. It's just examples. And so that's the main content of this book. Chapter 1, not shown, is a general introduction. Chapter 10, not shown on here, is what's the future of DSM possibly looking like, at least as of 4 years ago. So this is kind of the order we're going to use for this tutorial today as well. I'm going to talk about product and then organization and then process, DSMs in that order, then mention a few things about DMMs and MDMs. We don't have a whole lot of time, just about 1 hour left now, so I'm going to go pretty fast. So I'm going to leave it to you guys to stop me with questions if it's too fast for you, or if you just are curious about something along the way. Feel free to do that. I can adjust this to your interests. And by the way, does everyone have a hard copy of the presentation? If you need one, there's a couple places along the way where we're going to stop and let you practice writing a DSM. So it's one thing to look at slides and listen to me talk about DSM. It's another thing, can you actually draw one yourself? And so we're going to practice that a couple times along the way. So DSMs existed really before they were called DSMs, but the term design structure matrix comes from the 1960s. A fellow named Don Stewart, who has been to most of these DSM conferences. This is maybe one of the few he hasn't been at. developed this at the time, he was coming out of computer science, and he was trying to solve systems of equations. So if you remember linear algebra, Gaussian elimination, some of these techniques to try to find, okay, which variable do we determine first in the system of equations so that we can then find all the others. Well, there, of course, are better and worse ways to do this, and it's essentially a sequencing problem. So you want a sequence where you have the minimum number of feedbacks, because where you have coupled blocks of these variables in systems of equations, sometimes you have to iteratively converge on a solution. And so he was trying to solve these using matrices, and that's where this idea for design structure matrix came from. So he put out a couple of corporate reports in the mid-1960s, but outside his company didn't get a whole lot of attention. There's not many citations of these, and it wasn't until 1981 that Don Stewart published a paper and a book on design structure matrix. But even that, it didn't seem to get a lot of traction either. It wasn't until the late 80s and early 90s that there started to be a lot of work done with design structure matrices. And most of this work initially happened in two places. One was at NASA, where some NASA engineers picked up this idea and started to work with it in the late 80s. And the second was at MIT, where Steve Eppinger and Dan Whitney picked it up, and a few grad students started to do some projects with DSM. And so that's where some of these names you'll see referred to here, like Thomas Pimler and Kent McCord. These were master's students at MIT in the early 1990s, and have now developed what have become some classic, famous DSM examples. Get used quite a bit. And so then later some PhD students, including myself, came along and started working with these in the mid-90s, and then since about 2000, people all over have started working with these. In the early 90s also, I should mention Boeing independently picked this up as well, and started doing some internal development of DSM methods and tools. They didn't necessarily publish most of what they were doing. They considered it proprietary for the most part. So that's the case I've seen, is that there are a lot of DSM applications published out there, but it's just the tip of the iceberg, because a lot of companies use and apply DSM but don't necessarily tell people about it, because what incentive do they have to do that? They just use it because it works for them internally. They don't need to go present at conferences to benefit from it. So there's a lot more going on than we realize. But these are some examples of static DSM applications. These are some examples of temporal DSM applications, and also related techniques, things that you'll often see doing the same things under slightly different names, for example. So Don Stewart coined the term DSM. That term has kind of become a larger umbrella term for a lot of matrix-based techniques that are out there. Precedence matrices, these particular names, wrote some papers on these in the late 1960s. Totally unrelated to DSM, but essentially doing exactly the same thing. So some of these matrix-based techniques, people would represent a system or a network as a matrix, but then they wouldn't necessarily do anything with it. Just say, here's a way to show this, but there was no analysis. And so the benefit of bringing a lot of these disparate tools, but related tools, together is that now we can benefit by cross-pollination. Methods that have been useful one place, we can start to look at more widely. And so design structure matrix is now much bigger than it was when Don Stewart came up with that term. He essentially came up with that term for just the process DSM. So it was a while before Don finally agreed that these static DSMs, as we referred to them, were even able to really be called DSMs, because they didn't fit his original definition, which was a temporal DSM, a process DSM. And so there's a bit of history here. And if you're interested in these names, these citations, full references, I can give you some more information here in a minute on where to track those down. Most of them are in the book that is being passed around. There's also a paper you can download that you can get all that background information. All right, here's some examples of places where DSM has been applied, and these are just ones that I'm aware of, not even necessarily all the ones I'm aware of, just examples. And then there are many more, I'm sure, where it's not public information. But it has been nice to have this annual conference. It's provided opportunities for a number of industries over the years to talk about DSM applications. So I already mentioned what we're doing in the tutorial today. I will say that all of these examples I'll give you are taking what is essentially a generic modeling approach here that you can see. First of all, we have to decide what system we're modeling, and explicitly or implicitly we're putting a boundary around the system when we do that. But it's not always easy or obvious where that boundary should be. So this is your first modeling choice when you're modeling a system, is deciding what the system you're modeling is and what parts are included in it and what parts are excluded. Or we sometimes say endogenous or exogenous. So that choice right there can make a difference in what kind of model you get, what kind of results you get. So once you decide what that boundary, what that content of the system is, then you want to understand connections between the system and these external or exogenous elements. So you've made a choice not to include certain things in your model, but you still may want to be aware of connections to them. And so that's something to keep in mind. Third thing is deciding how far to decompose, break down what system you're interested in into smaller pieces, or nodes that you can look at relationships among. You want to describe characteristics or attributes of those elements, and then you want to look at the relationships among them. And again, you may want to describe more than one attribute of those relationships. So several modeling choices and decisions getting made along this process. And then finally, you do some analysis. And this analysis is typically some kind of rearrangement, some type of regrouping or reordering of the elements to expose or to create some kind of patterns like modules or cycles, or maybe to eliminate something like cycles. So there's some desired and some undesired system behaviors that you're trying to affect or influence by changing the architecture or structure of the system. So this term design structure matrix, sometimes we think maybe it's not really the ideal term for what we're really doing here. So what does this term really mean? But I think if we can imagine we're trying to look at the structure of the design of a system in a matrix format, it does make some sense. I think it is maybe not the ideal, but it's still a reasonable and meaningful term for what we're doing. So I said you could get more information on all these references and names that are being put up here. The book is one case. This paper you can download from my website. So it has a bunch of background references. There's also a newer paper that I mentioned earlier today, just came out a few months ago. That paper you can also get on my website, maybe not in the final published form unless your technical library gets the IEEE journals, but you can get the same content in a kind of unpublished form there on the website with all the references. All right, so product architecting. That'll be our first DSM application. And here is a abbreviated version of that same general process I just showed you a minute ago. First, we're going to take our system as a given, and we're going to break it into pieces. Here we'll call them components of a product. We're going to look at the relationships among those pieces, and then we're going to see what sort of new integration or structure of the architecture we might come up with based on that model. So one of the most common ones is something called clustering, where you're essentially trying to group related elements together in clusters and separate unrelated or less related elements into different clusters. So step one is essentially like a product breakdown structure or a bill of materials. It's a hierarchical decomposition of the pieces, and depending on where you work, you may use different names for different levels of this decomposition. So you might even go another level to what we call components sometimes. You may use different names, but the idea here is that we've got different levels of decomposition, and what we're trying to do is figure out what level we want to go to, and that's the choice we're making about level of decomposition. Sometimes we may stop at a higher level and say that's sufficient. Sometimes we may need to get to a lower, more granular level. Step two then is finding the relationships among these components. That's where DSM is going to come into play. And then step three is assigning or grouping these components or whatever level we're at into groups, clusters, modules of some kind. So steps 1 and 3 you can look at with this hierarchical structure, but what this type of breakdown structure does not tell us is what are the relationships among these components at a given level in terms of input-output, in terms of being next to or away from each other, or some kind of transfer of energy. We don't know that. So step 2 that's missing here is where we document that, and that's where the DSM comes into play. So here's an example of a product architecture. This is an automobile climate control system, one of these classic examples that Thomas Pimler and Eppinger did originally. This is from Ford Motor Company. And this is not exactly a binary DSM. This is a trinary DSM. It has 3 possible relationships. Either no relationship, which would be a blank cell, or a weak interactions or strong interactions, depending on. So now we're starting to see you can have more possibilities than just yes, no for a relationship. Notice that we want to give names to these elements, and so often those are written in the rows over to the left. Sometimes they're written also or in the columns above, but there's usually not room to put them in these small cells on the diagonal. So that's where the letters come in as a shorthand. Sometimes you see just the letter there along the diagonal. Sometimes you label on both sides. Sometimes you can label on the bottom and the top, but you don't have to. So you just see there's a lot of options, a lot of customizations, a lot of ways you can choose to add or subtract notation here on the matrix. But the point here is to try to document all the relationships. And a lot of times in examples like this, we just show this and move on, but I will comment that that's not always easy to do. That capturing and accounting for all of the relationships among elements is not always easy, especially the first time you do it. So you can imagine a complex product that, yeah, you got the obvious relationships, maybe I'll say the planned relationships captured in the model, but later on discover that maybe some component vibrates in a certain way, and that vibration transfers in an undesired way to some other components. And that's not shown here as a relationship, but should be. And so these models can and should improve over time and capture more learning about the system, but that's not always the way they're used. So I'll just, as a warning, a caveat, the first time you build any system model, DSM or not, be suspicious of its accuracy and completeness, because complex systems are hard to understand all that's going on in them. But this is the example of step 2, documenting relationships. And before we go on, talk about what we'll do next, I put this in there so that these next 2 slides could be on the same page for you. And this is your first chance to practice writing a DSM. So what I'd like you to do is to draw a DSM on slide 18 of this system on slide 17 that's represented by what's called an architectural block diagram. And hopefully this diagram is intuitive enough that you'll be able to see what type of DSM you should draw down below. But if not, feel free to ask me questions. So try drawing a DSM of this system. First question you need to answer is, how big should the DSM be? So what's the answer? How big should this DSM be? Okay, good. Okay, 4 or 10. Yeah, it depends on the level of granularity you want. You're exactly right. And so let's draw a 10 by 10. Let's use all the information that we have. If we used a 4 by 4, we would be correct, but we would be ignoring some additional information about the system that is available to us. So let's go ahead and use all the information that's given to us and do a 10 by 10 DSM. So work on that for a minute, draw that. And when you have questions, let me know in the square matrix. So what could you do with them? That's a good question. And let's look at an example answer here. See if we can get this on full page. All right, here's an example answer. Compare this to what you got. Now, you may have listed these components in a different order. And if you did, that's okay. But it won't look exactly like this answer. But if you'll notice here, we have both our 10 by 10 DSM, and if you kind of step back, we also have the 4 by 4 DSM, right? Because here's 1, 2, 3, 4 components viewed from a higher level. So you see that this architectural block diagram was a nested diagram showing components inside subsystems inside the bigger system. And the DSM can do the same thing. So here's an example of using shading of the diagonal cells to help indicate subsystems or groupings or modules. Sometimes that's done with just a thicker block line in the matrix, no shading. Sometimes it's done with shading over here of the names in different color groupings. So there's different ways you can show membership in a module or a subsystem or a group if you want. Any other questions about this or why it might be different from what you have? Or yeah. Turned it around. Why turned it? So what we started with was we had outputs in rows and inputs in columns, or was it the other way around? Look back at slide. Inputs are in rows and outputs are columns. Yeah, this one has inputs in rows. IR, that's what that's saying up there at the top. IR convention means inputs in rows. And so that's what this is. It should be inputs in rows, outputs in columns. So if that's true, then this should have an output from antenna console as an input to antenna control computer. Is that what we have in our diagram? So that's what it should look like. Now later I'm going to explain that you can do the equal and opposite convention where you have outputs in rows and inputs in columns. And that would be IC instead of IR convention. And I'm going to explain the difference and why that exists later. But for now, yeah, we're doing inputs in rows, outputs in columns. Again, each dot here represents an arrow, and it's both an input and an output, depending on your point of view, right? So it's an output from one and an input to another. So as long as you have arrowheads in your block diagram telling you the direction of the relationship, you should be able to decide if it's below or above the diagonal in the DSM. More questions? Now is a great time to ask really simple, basic questions. Make sure you're comfortable with this. Everybody get, or at least understand why you didn't get what is here? If you're still unsure, just ask, and we'll go over it. Yeah. Right here? Yeah. Uh-huh.
It's an input for antenna.
Yeah.
Is that it?
Yeah, antenna and mount. It's an input, right? We're saying the inputs to each thing are in its row. Okay. Inputs in rows. So 2 arrows go into this component, antenna and mount. One of them comes from antenna control computer. The other comes from VHF transmitter and modulator. So that's how to read it. Good question. More questions? Question? Okay, you got it? All right, well, we'll move on. All right, so a next step that can be done to make the model richer, add some more information to it, is to start looking at these relationships instead of just weak or strong. We might look at different types of relationships. We might look at even more levels or strengths of relationships. So for example, 4 different types of relationships among product components here that we could look at. And it's not necessarily comprehensive, it's just 4 example relationships. So spatial relationships, maybe they need to be co-located, or maybe they need to be separated. That's one type of relationship. Another type might be a transfer of energy or information or material flow. So these are different types of relationships or interactions. And we might want to distinguish really strong, desirable, necessary relationships from weaker ones, from negative relationships even, or undesirable relationships. So these are possibilities that we might or might not want to put in the model depending on what type of questions we're trying to answer, what type of decisions we're trying to support, or what type of insight we would like to get. So going back to that automobile climate control system example, here now we have just a subset of the relationships. This matrix is not as dense as the one I showed earlier. that had all of the relationships. This is just the material flow relationships. So some of the components are not involved in those, so they have a blank row and a blank column in this particular DSM. And then furthermore, all the material flow relationships now are categorized on that scale of +2 to -2, and it just happens here that all of them are strong, desirable, necessary relationships, so they all have a number 2, +2 here. So we use this now, and we're going to show what is meant by clustering, which is one of the typical analyses that we'll do. And in this case, you notice that all of the elements or components with blank columns and rows, they're just kind of pulled off to the side. In this case, the upper left, sometimes it's the lower right. And then the remaining ones, are the rows and columns, are reordered to try to group together along the diagonal clusters or chunks or groups of related or similar or some other way desirable to be associated together components. So often these are called modules as well. Notice here also that there are a couple of components with memberships in 2 modules rather than 1. This is what we call overlapping modules. And I mentioned earlier today that clustering algorithms don't always allow this or suggest this. Sometimes you have to, the clustering algorithm is going to take a component like this, and it's just going to make a choice whether to stick it in this module or that module. It doesn't necessarily know that maybe being in both is a possibility, unless it's a really sophisticated clustering algorithm that knows to do that. So that's the idea of clustering, but sometimes it's easier said than done, or easier just to show a nice result than to get there. So what's happening in a clustering algorithm? Well, as I had also said earlier today, a lot of things could be happening, and there's a lot of different possibilities. But perhaps a very basic, simple way to explain an objective function for clustering is this example here, where you're trying to minimize 2 things combined. One is you want to minimize the number of clusters, but you also want to minimize the size of each cluster. I mean, there's some trivial solutions to this problem that you usually want to avoid. One of the trivial solutions is put all the elements in one big cluster. That makes all the interfaces what we call intra-cluster relationships. They're all within the cluster, which is usually desirable. We penalize inter-cluster relationships, relationships that remain outside of the cluster definitions. And so the trivial solution with a naive clustering algorithm, an objective function, would be just to put everything in one big cluster. At the other extreme, it's to make each component separate, its own little module, its own separate cluster. And that's also undesirable, even though that minimizes the size of each cluster. And so here we have 2 things together, and we're trying to optimize both at once. And so these are essentially competing objectives here. One's trying to minimize the size of the clusters, and the other's trying to minimize the number of clusters. And it's penalizing interfaces that remain outside of cluster boundaries. So this compares an unclustered DSM example with a clustering result that has 2 non-overlapping clusters. Here's the first one. Here's the second one. You see it's one huge cluster and one small one, and 2 relationships outside of these cluster boundaries. And when you plug in this particular objective function, you get a number 880. It's only meaningful in a relative sense. If you're trying to minimize, here's a number 760 that's smaller, so it would be more optimal. And notice here, It's mainly because we took that 8x8 cluster and broke it down into two 4x4 clusters, which, since the size of the cluster is penalized quadratically, taking from 8 to 4 is a big improvement, despite the additional penalty of having now two more marks outside of the cluster boundaries. So you see, clustering is not really so simple at times, and this is just a binary DSM. So how do you start accounting for different weights or importance levels among the relationships, or different needs for components to be together or to be separate in different modules? These are additional considerations. Should you allow overlapping here rather than try to make these B and E go into either one module or the other? Should you just allow overlapping here? Those are additional questions, but they require more sophisticated objective functions. So the idea of clustering is pretty simple and straightforward. Actually, doing it right, doing it well, isn't always so easy. There's a lot of possibilities there. So a few things to consider here. I've mentioned up at the top there. And then notice that we just clustered the material flow interactions from that automobile climate control system. Maybe we get a different answer if we cluster just the energy transfer relationships. And maybe we get yet another answer if we cluster just the spatial adjacency relationships. And maybe a different answer if we try to cluster that original DSM that had all the types of relationships at once. So again, is there really one right optimal answer? Not usually. Usually there's a lot of competing criteria, and you're trying to come up with some result that, rather than really optimizes anything, just kind of satisfies everyone at some level. And often the idea here is to generate different alternatives or possibilities and then start comparing them, start evaluating them. Some of them may not really be feasible, in which case you may need to go back and introduce some more constraints into your model, and then try the optimization again. And so often this idea of building the model, analyzing the model, optimizing the model, it's a very iterative process because you're improving the model as well as the answer you get along the way. And so that's something that, to do this well, you need some good knowledge and intuition about the system you're working with, not just be someone who can make matrix models. One other thing to mention is sometimes you'll find elements in a product DSM that are highly integrative, highly interactive. And you might need to just pull those aside, remove them from the clustering algorithm, because they essentially interact with everything else. All right, so we're about out of time in the big picture, not just with product DSM. So what I'm going to do is point out that you've got some information in your packet here. I'll call it FYI stuff on clustering tools and some more examples that I'd go through if we had more time. These examples are also in the book. Some insights, some places for more information. And if we had more time, I would go through an org DSM example, but it is also a static DSM. And so it's very similar to the product DSM we've just been looking at. And so I'm going to skip that one because of our time constraint. This example is also in the book if you want to have a more thorough look at it. And in the time we have left, I want to make sure we introduce process DSM, since that's one you're likely to see some of in the upcoming presentations. And just make sure you're familiar with how that's different from the product DSM. So for this one, we'll start with a real simple process. You may have done this process this morning, getting and putting on socks and shoes. So 5 activities, and some deliverables or work products coming out of and going into these activities. And we can show this as a DSM, where now we have what we call upstream activities or initial activities in the process in the upper left part of the DSM, and then downstream or final activities in the lower right of the DSM. And here we have a potential feedback or rework loop if we don't pass our inspection. Maybe we get our shoes and decide they don't look good with these clothes, or they're messed up somehow. We got to go back and get shoes again, do some rework, do an iteration in our process. So that's one possibility here. And you don't have to show it this way, but this is shown as a diamond just to indicate that it's a potential, not a guaranteed relationship. But not all DSM models use a different symbol to show that. The fact that it's above the diagonal is really enough to indicate that there could be a feedback. So you've got some more information on that. And here I should mention the other convention where we've been working so far with inputs and rows. And as a result, feed forward with a temporal DSM would be below the diagonal, and feedback would be above the diagonal. But there's another convention, which is just the transpose of the matrix, where the inputs are in columns, and this makes the feedback marks appear below the diagonal instead of above. And so important thing is that the two conventions are equivalent in terms of the information they show. One reason for this other convention, where the feedback is below the diagonal, is that it helps orient the external input and output regions that sometimes get put outside the DSM. And then it's also intuitive, and it's the convention they use in systems engineering. So it also kind of fits well with Gantt chart and IDEF models that some have been used to working with. So for a number of reasons, this other convention exists, and here's what it looks like with our socks and shoes example. It's just the transpose of the matrix. So same number of marks off the diagonal. It's just that the marks that were below the diagonal are now above the diagonal. So the output's in a row and the input is in a column instead of the other way around. So now our potential feedback mark is here, from inspect shoes to get shoes. And this convention allows us to add a couple of regions outside the DSM. These are not always used, they're optional. But here, if we have a process with 5 activities, we have, for activity 1, some inputs in its column that are not from other activities within the process, but are from external activities or other processes. And then we have outputs from that activity that go to downstream activities within process A, but also can go to some other external recipient. And so we can just keep reading in the columns to see inputs. We can keep reading the rows to see outputs. And so these optional regions can help define connections to outside the system that we're focused on. And so in our previous exercise with the architecture block diagram, we had 3 arrows leaving the picture. We could show those over here somehow in a diagram like this. So this is our second DSM exercise. We don't have a lot of time left, but I'm not going to let you do it now, but I encourage you to work on it at the break if you'd like. If you want some more practice, you've got a place to do it. You've got some external inputs and outputs and a place to show them. And this will also let you practice this input and column feedback below the diagonal convention, which is different from the one you learned a moment ago. So you can work on that later. for now, I'm going to skip ahead and just highlight some general activity relationships that you can typically see in a process DSM. So your classic dependency of activity 2 on activity 1. And notice here we're back to our input and row feedback above the diagonal type convention. We've got 2 activities that have no direct relationships, so they're independent activities, and if we have enough resources, we might do them in parallel. We've got interdependent or coupled activities. So these are the chicken and egg problems. And by the way, sometimes these problems go away if we drill down and model these 2 activities at a deeper level of decomposition. You can imagine at a high level in, say, a product design process, all of the activities are related to each other. But when you start breaking down into smaller activities, you can start to see more of a sequential flow among them. So that's often the case. And then here are an example of contingent or conditional activities where we might do one or another depending on the result from an upstream activity. So the analysis for process or temporal DSMs is something we call sequencing. We're reordering the rows and columns, but this time we're not necessarily just trying to cluster. We're trying to minimize feedback marks. And so what that looks like is we'd like to reorder the rows and columns to try to get any marks, in this case below the diagonal, to either move above the diagonal, or if we can't do that, get them as close to the diagonal as possible to minimize the length of the feedback. And I'll show you why here. So here's that reordering. In this case, it's moving that inspection step upstream so that it occurs right after we get the shoes. We inspect them immediately. So in this case, we can't get this feedback mark above the diagonal because if we move the inspection step even further upstream to get this mark above the diagonal, this mark here would take its place down below the diagonal. And intuitively, it's hard to inspect what you don't have yet. So there are limitations, and the DSM, if you build the model correctly, will put those type of constraints in here. And so here, notice that with the previous original model, if we inspect shoes, we not only have to go back and get shoes again, but we potentially have to rework other activities, interim activities, that were done based on the assumption that those shoes were the right ones. So this is not just what we call first order rework of getting new shoes, but potentially second order rework of putting on those shoes again as well. And so by getting the feedback marks closer to the diagonal, we're minimizing that second order rework that we'd otherwise have. So you can imagine a mark in the lower left with this convention or the far upper right with the other convention would be the worst possible case. You're going from the end of the process all the way back to the beginning, and that may also imply having to redo a bunch of things along the way as well. And so what you'd really love, if you've got to have feedback marks, is for them to be close to the diagonal so you can immediately find and fix any situation that needs rework. This minimizes cost and schedule risk in the process. So here's a basic message. I call this the executive version of the chart. So try to not have these problematic feedback marks that represent rework. Often it's unnecessary. Often it's an artifact of just doing the work in the wrong sequence, making decisions in the wrong order, or something like that. Solving your system of equations without starting with the right variable. So here's another example, this time an automobile design process got a bunch of activities, and when we apply that initial sequencing algorithm, we either move some of the marks above the diagonal, the remaining marks we've moved as close to the diagonal as possible, and furthermore, we've grouped what we call coupled blocks or circuits of activities together. Now, people, when they first see this, they might get confused with clustering. Because before, we were clustering blocks along the diagonal as well, right? But in that matrix, it didn't matter if the mark was above or below the diagonal. Static DSM doesn't matter which side of the diagonal the mark is on. It's only with the temporal DSM here that we start to care about whether the mark is on one side of the diagonal, the feedback side, or not. And so here we have a pretty good sequence of work to prescribe, with a couple of exceptions where we're going to have to deal with some more complicated management issues, coordinating and integrating several activities. But these things called coupled blocks are often what we first want to identify, so we can highlight their existence and then come up with some strategies to deal with them. So some of the things that can be done for coupled blocks are shown here in number 2, something called tearing. We can do additional decomposition, like I mentioned. You can also just do what's called aggregation. So, for example, if we take these two activities here and we just combine them into one activity, that makes that feedback mark disappear, right? So we solve that problem. Thing is, it's like sweeping the problem under the rug. It's still there. It's just we don't see it. The whole point of this is to illuminate and expose those situations, not disguise them. Even though I've known many people when presenting to management who have kind of obscured some of the inconvenient messages in these types of diagrams. But the point is to solve the problem, not hide the problem. So an example of solving the problem here, we've got a 2x2 DSM that's a coupled block, chicken and egg problem. What should come first? But when we further decompose the first activity into a 5x5 and the second activity into a 10x10 DSM, and we decompose these relationships into finer grained relationships among those constituent activities, now we apply a sequencing to this model and we find, hey, it's easy. There's no real coupling, no real feedback mark. The only reason it exists is because we're treating work, we're treating the teams doing that work as monolithic blocks, not understanding the more detailed relationships that those teams doing that work should have. And if we can go in and define the work in a greater level of detail, we can often find, okay, some of the work from one team or a decision by one team needs to happen, then some work and decisions by the other team should happen next, and then it's back to the first team to do some more work, make some more decisions. And if we understand that process well enough, then we don't necessarily have to iterate to find a solution. But it would look like iteration if we just took these original two teams and told them, hey, go work together until you figure out how to do this. So an idea here is that there is a lot of unnecessary iteration and rework in a lot of projects and processes. That these type of models can help illuminate and eliminate. There's some more advanced techniques here as well. There's examples of some of these in the book, like process failure mode and effects analysis. This example from Intel is a pretty classic one as well. So a 60x60 DSM of tasks in the design process for a computer chip. And here we have feedback above the diagonal. We have some recognized and planned iterations, rework loops among some coupled activities. But then we also have out here a lot of potential failure modes in the process that might send us back to do rework upstream. And all of these were not recognized or known initially, but over time, as they do more projects, they start to learn what ways the project might go wrong and capture these as potential failure modes so that the next project can be aware of them. And now when they're doing certain activities like this one that have a lot of potential ways that future results could come back and make them change what they did originally, they do their original work, their original design decisions in a more robust way to minimize the chance that something later will need to be done differently. And if it is, so that it'll be easier to do that thing differently. So there's a lot of potential benefits for these type of models besides just minimizing or eliminating feedback marks. So some applications for these process DSMs noted, some tools that you could be aware of, some insights, more information, papers. Some of these you can get on the internet, some you have to go to your library to get. So we're officially out of time, but let me take just a couple more minutes to say quick things about DMM and MDM, because you're going to see some of these in upcoming presentations. So we've got our product, DSM, we talked about that. We've got our process, the work that we do to get that product. And by the way, we can make this more generic. We can just say this is a result system for any project, and then we've got a process of activities that we're doing to get that result. So this doesn't have to be product development specifically, even though that's kind of what this example focuses on. And we've got people, teams assigned to do that work. We've got tools, resources that we use to do that work. And then we've got goals, requirements that can affect all of those systems. And we may even have multiple projects or programs going on, each with this combination of things inside. And so it's important to look at and try to analyze and optimize individual ones of these systems, but as you can guess, sometimes the optimal process doesn't create the right product system. Sometimes we're constrained by some general process that the organization we're part of wants all projects to use, common process. Maybe we don't have the freedom to completely change it or optimize it the way we like for our project. Maybe there's some common product platform or architecture that several projects have to adhere to. So maybe they don't get to change that the way they would like for their project. Maybe there's common tools that the whole company wants all projects to use. So each of these systems affects the others. Sometimes it limits, constrains the others. And so truly optimizing any one of these systems, it's an interesting case study and presentation, but it's not clear that it really improves the overall project or enterprise unless we step back and look at the bigger picture, look at the context around whatever it is we think we're optimizing, and think about, okay, how would changing the system and the way we're thinking with clustering or sequencing, does it have any effect on the rest of these systems or projects? And are there any constraints from the rest of these systems or projects that limit our ability to modularize or sequence or something like that? So that's a challenge where DMM and MDM can potentially start to help us. So DMM is a rectangular matrix that just maps from one domain to another, such as assigning people or teams in an organization to activities in a process. So some kind of responsibility assignment matrix or RACI matrix, as is commonly used in project management. Very common example of one of these. So this is a collection of DSMs and associated DMMs that might exist out of those 5 I mentioned before. Not all of these have been created necessarily. Just like the periodic table, maybe there's some blanks that you discover a new element because you infer its existence based on the others. So this combination or aggregation of multiple DSMs and or DMMs has been called a few things, but the name that's stuck is multi-domain matrix. And so this is something that Mike Maurer came up with as part of his PhD work about 10 years ago. And it's stuck. And so when you hear MDM, think of combinations of several DSMs and DMMs. So I put some examples in here, but I don't have time to go through them now. But they're in the book if you're interested. So some of you have this book, some of you looked at this book. If you're interested in it, of course, there's always Amazon as one possibility. You can also get it from MIT Press, which is the publisher of it. And I have a couple copies here with me that if you're interested, come talk to me and I'll save you shipping. So I'm going to go ahead and cut off the time now since it's break time, and I don't want to stand between you guys and break. But if you do have questions, feel free to come talk with me at break or any time, and I would be happy to do that. So thank you for your time.